In the previous video, we looked at energy sources. We classified them into kinetic and potential, and then classified or subclassified various types of kinetic and potential energy. Today we're going to look at one of those classifications of energy, which is electricity. This electricity video will actually be split into two videos, one on just an introduction to electricity at an atomic level, and then on a second one looking at electrical circuits. So electricity is a phenomenon that exists due to the structure of matter. It's due to matter being made up of electrical charges. Electrical charges are part of the structure at the atomic level. So let's look at electricity at the atomic level. First of all, and a lot of this should be reviewed from physical science, we have elements. Elements are the simplest form of matter. There are actually 118 of them. This particular periodic table is a little old. Now I have them all the way out to here with 118 known elements at this point, and that will also change within a few years more than likely. For these elements, the simplest form of matter, each element is made up of a type of atom. An atom is the smallest piece of an element that contains all of the properties of that element. Now, atoms are made up of smaller parts, but the smaller parts don't have all of the properties of the individual elements. In fact, the parts coming from different atoms would have exactly the same properties, but the arrangement of those smaller parts gives the atom its unique properties. So let's look at those smaller parts of the atom. The components of the atom would include the nucleus, which is in the center of the atom. That's the most important part of that. Central portion of the atom, and it contains two different kinds of particles, protons and neutrons. Our protons are positively charged, so I often use the symbol P+ for proton, and our neutrons are uncharged or neutral. I usually use the symbol N with a 0 for the neutron. But both of these are packed into a very tight nucleus. This atom that's shown over here is not really to scale. The nucleus would be, for an atom this large, is barely visible in the center, occupying a very small amount of space. A value that we can give to atoms that defines the atom is the atomic number. The atomic number, first of all, is found on the periodic table. In each block for each element, there's a whole number. Hydrogen is 1, helium is 2, lithium 3, and so forth. And those whole numbers tell you the number of protons in the nucleus of an atom. Okay, so it's specifically defined as the number of protons. And you can see when you look at a periodic table that elements are arranged on the periodic table according to the number of protons, or the atomic number. The atomic number identifies the element. If something happens to the atom of an element that causes its number of protons to change and its atomic number changes in response, then we actually have a new element. So how many protons in this nucleus? A little bit difficult to see the diagram, but we can say we've got a proton here, 2, 3, and 4 protons. So this would be a 4. We also have electrons, which are negatively charged particles. They're identical in charge to the proton, except they're opposite in sign. So the amount of positive charge that a proton has is the same as the amount of negative charge that an electron has. Electrons are outside the nucleus in a space that we would call the electron cloud in most modern representations of it. But we would say that the electrons are in spaces in this electron cloud outside the nucleus known as orbitals. And orbitals are orbits in which electrons move around the nucleus of the atom. This particular model of the atom shows them as ellipses going around the atomic nucleus, which is not really the modern view of the atom. Our electrons can occupy many different orbits or spaces, but the ones that are in the outermost ring, the outermost orbit, are known as valence electrons. And for instance, in this, we have 2 energy levels, or 2 orbits, and we would say that we have 2 electrons in that level. So we have 2 valence electrons, and these rings are called energy levels. This is number 1, this is number 2. Energy level 2 is the valence level. Valence level would be the highest level, the highest number, farthest away from the nucleus, that has electrons occupying it. So, how do you understand something that you can't see? And how do you describe it? Well, you have to develop something known as models. And over hundreds of years, scientists have generated mathematical models to describe the structure of atoms and how the particles interact, and also how the structure of atoms gives rise to their physical properties and the properties of materials, which is very important to this course. We have multiple models that are currently being used at some level. The oldest of those is the Bohr model, named after Niels Bohr. And this negatively charged particles orbit around a nucleus. So here's our nucleus, and then we have rings like the solar system, and the electrons are in those rings. This is sometimes called the planetary model, although this is really a little bit more modern version of the planetary model. We have the electron cloud model, which instead of having electrons in definite spaces and rings, describes the location of the electron in terms of a probability. We have a chance of finding the electron at a certain location, and we can calculate that chance, where the electron is likely to be found. We also have the quantum mechanics model, which is mathematically describes the interactions of atoms at a nanoscale. Really, these two are hard to separate. The modern electron cloud model is going to use quantum mechanics, which is well beyond this particular course. It's important to note that each model has its own good parts and also shortcomings. The best model is probably not the one that we're going to use, but every model has certain parts of it that, if you use it appropriately, tends to describe what we see. And that's the most important thing. So even if it's not completely accurate at all levels, it's likely going to be accurate at a level where we're going to use it. We're most interested in the outermost ring, where the valence electrons are located, because they strongly influence the properties of elements, and therefore the substances that elements make up, which is pretty much everything. So in the following slides, we're going to have examples that use the Bohr representation, this one, rather than the electron cloud model or the quantum model. And as you continue to study chemistry, as you study it in more depth, you're going to learn that the periodic table, the shape of it, the structure of it, says something about electron arrangements of elements based on what we understand about atoms at this point. Electron configurations, which electron configuration just means arrangement, and consequent location on the periodic table identify an element's properties. So, for instance, we would say that sulfur right here has certain properties, and those properties are unique to a location that's here on the periodic table. And we may have properties that are similar above it and below it. And we start to deviate as we move from the left to the right or up or down. The farther we get away from it, the more the properties are going to change. But electron arrangement is the basis for the periodic table's shape. According to Bohr, the electron orbits, and remember, I actually prefer the term energy level. The orbits around, or the energy levels around, are occupied by a certain number of, a maximum number of electrons. That maximum number is given by the equation 2n squared. Again, this is part of Bohr's model. So if we have 1 squared, or 2 times 1 squared, that equals 2 electrons. So if we have 2 times 2 squared, 2 squared is 4 times 2 is 8 electrons. And then if we have 2 times 3 squared is 9 times 2 is 18, and so forth. We can calculate in whatever energy level we need what the maximum number of electrons is going to be. The orbits that, if we had a empty atom, a naked atom with just a nucleus, and we were going to put in electrons into it one at a time, those electrons would fall to the lowest energy state, which is energy level 1. Once it has 2, we're going to go out and fill the second energy level. The pattern of filling is somewhat more complicated than that, but for most of the elements that we'll deal with, we will assume that always the electrons are going to fall to the lowest energy position that's available to them. So electron orbits or energy levels have certain tendencies that tend to show up when we observe them and describe the atoms. Atoms like to have 8 electrons in their valence level. By like means it's their natural tendency. Atoms don't like anything. They don't have brains to like things with. So when we look at something like 8 represents a particularly stable arrangement. This is the same number that all the noble gases, with the exception of helium, all the noble gases would have these 8 electrons. 8 electrons, by the way, in case you ever see this term, this is known as an octet, a set of 8 electrons. So the noble gases are very stable and low energy, and that's where atoms like to be, low energy and as stable as possible. And 8 electrons for most atoms is going to represent that stable number for their valence level. Here we have copper, and the question that we would ask here is how many electrons are in the valence level. Well, the valence level, and you may not be able to see the portion below this, but it's just a repeat of this, more electrons here. The valence level is this one, which we're 1, 2, 3, level 4, energy level 4. And we can see we've got 1 electron there. Okay? So the question is then, is copper a conductor or an insulator? By practical experience, you probably know that copper is a metal, and that copper is used in wiring, and of course if we're using it in wiring, it must be a conductor. So the question is then why? Why is copper a conductor? And we'll answer that question as we move forward. Then we have sulfur, which is a nonmetal. And again, we're going to ask the question, how many electrons are in the valence level? The valence level is 1, 2, energy level 3. And we've got 6. So is sulfur a conductor or an insulator? And the answer is that it's an insulator, as are most nonmetals. In fact, we'll say all nonmetals are insulators. That's one of their properties, properties of a nonmetal. Properties of metals is one of the properties, at least, is that they're conductors. One of the properties is that they're of nonmetals would be that they're insulators. So the question again is why? And the answer to the question comes down to what elements have a tendency to do. In general, metals tend to have very few valence electrons. By few, that's usually 1 to 3. And they have a weak hold on their valence electrons. So they have very few of them, and they hold on to them weakly, while nonmetals tend to have higher numbers of valence electrons and relatively strong attraction for them. So they hold on to their electrons more tightly, and that higher number is usually 5 to 8. Although you'll notice we don't have 4 in here. 4 could also be included in most cases in the nonmetals, but in a few cases, like lead, for instance, and tin, we may actually have metals with that level. So the 4 valence levels, or 4 electrons in the valence level, is sort of a transition number. So when metals and nonmetals are brought together, there could be a transfer of electrons. So metals would lose because they have weak attraction, and metals would gain. And so we have electrons transferred from metals to nonmetals. Excuse me if I left that non out. And in the process, both the metal and the nonmetal will acquire 8 electrons in their valence level in most cases. If pure metals are brought together, and you may not again be able to see down below this, but if pure metals are brought together, there's no tendency to exchange electrons. There's no attraction of electrons of one metal atom to electrons more so than another. So if we have, for instance, if we have pure copper, we're not likely to see one copper atom attracting electrons more so than another because their attractions should be essentially identical. So pure metals have a tendency, because they have weak control over their electrons, to just release them from their atoms. But then, when you release an electron from an atom, then you have a positively charged nucleus. So the end result is that we have a positively charged nucleus in this area called an electron C. So if you can imagine, we have nuclei in 3 dimensions. And so forth. And then we've got electrons that are everywhere in between all these nuclei. And the electrons are attracted to the nuclei, and the nuclei are attracted to the electrons, so they all hold together because of those attractions. That area, though, where the electrons are dumped into is known as the electron C. This is a region of free electrons. They're unbound by any particular nucleus, so that leads to them being able to move. They're not stuck in an energy level. So this leads to an ability for electrons to move more freely, and that makes for good conductors. If something's going to be a conductor, it has to have mobile, which means movable, charged particles. In the case of metals, it's going to be mobile electrons. Protons don't move. We have conductors and insulators. Our 2 possibilities for the elements that we'll deal with. Conductors, we have electrons that flow very easily between atoms, and the reason for that is because they're mobile. They're basically dumped off of atoms into an electron C. In insulator, the electron flow is more difficult, mainly because the valence electrons are held tightly by the individual atoms, and the electrons are not in an electron C, so they're not mobile. We tend to have, as far as the number of electrons, 1 to 3 electrons in the valence level, whereas in insulators we have somewhere between 5 and 8. Examples of conductors would be things such as silver, copper, gold, aluminum, and many others. It's actually the majority of elements that we know to exist. And insulators would include things, these aren't elements, but these are just materials, mica, glass, quartz. But if we were to look at elements, it would be solid elements would be things like phosphorus and sulfur, and selenium would be examples of nonmetal solids. And with that, we will end this first video.